So now we're going to look at another example of series LEDs. We got blue LEDs right here. Each blue LED needs about 3 volts just to conduct. That's the first thing to remember. We got 3 of them in series right there. So we're going to need a total of 9 volts just to get them to conduct. We got 12 volts at the supply, 1000 ohm resistor, so there remains 3 volts. Since each one of these drops 3 for a total of 9, that leaves a remainder of 3 across our 1000 ohm resistor, which means that we can expect 3 volts divided by 1000 ohms equals 0.003 amps. Make sure you do the math in amps, but after that you can refer to it as milliamps, 3 milliamps of current. Wattage isn't written on here, but it's pretty simple right there. That's the current times the voltage. This is how hot the resistors are going to get. With the LEDs, you just need to limit their current below 20 milliamps. But the resistor, you got to look at wattage. So that's current in amps times volt. Very simple. 0.009 watts. And so 9 milliwatts. Quarter watt resistors like these are rated for 0.25, but that's maximum. You should still stay below 0.125. And again, this will be a 9 right there, much less than 125 right there. So in any case, we'll zoom back. We can first do the simple look right there of the current the power supply is providing. 3 milliamps of current. It was saying 2 before, but probably a little bit more current is flowing now because semiconductors start conducting a little bit better when they get warmer right there. But that just means their voltage is going to go a little bit lower or whatever. It's going to go across the resistor and it's going to be limiting current. So at some point you'll get equalization. But also this power supply, if it's like 299 right down there, it'll just say 2. It's not as accurate as a multimeter. So now, speaking of multimeters, I just grabbed one. Well, I moved the jumpers up here out of the way. We actually don't need them. All we're using is that negative row and that positive row, but I try to keep those connected always, just in case. I turned the power off while I moved them, so I don't accidentally make a short circuit connection. So we got power back on. Now, when it comes to measuring voltage, this multimeter, it's really straightforward. I just got one setting right there, V. And this is a DC circuit. There's a positive and negative. If there's changing voltage going back and forth, you would put this to AC right there. But we're not going to measure a changing voltage. Looks like it was picking up changes in the air. So, in any case, there we go. We got 0 volts right there. And first off, we can measure the supply voltage, which over there is 12 volts. But that's a good starting point. First off, we can see how much voltage is making the circuit. So in the last circuit I did, this little bit of voltage may have given us less current than we desired. So that wasn't the only thing. We saw other causes for that. But in any case, there we got it. As I said before, these 3 LEDs together are going to need 9 volts across them. It's just a little bit lower right there, and so I thought it would line up with 9 volts more closely. So in any case, we can look at each one right there. So you can see, hopefully they're all got about the same voltage across them, but they can differ a little bit. So I'm measuring each individual LED, and the reason why, big reason why, somebody mentioned that in the last video when I had the red LEDs. I didn't measure each one of them individually, and they wish that I did. So we're going to look at the resistor. So it's going to have the rest of the voltage. We have a little bit less than 3 on each of these. So this one's going to be a bit more than 3 volts. And whatever the supply voltage was to the rail, and then minus the LED drops right there. So I'm not going to do the math. You can see that. So now what I'd like to do is measure current, and so it's okay to leave this on voltage. Probably want to turn it off, but in any case, we will pluck this little jumper because you have to bridge the gap where you measure current. And I didn't do this on purpose, but it lines up where I got the little measurement bubble on there. So now we got the jumper out of the way, and I had to kind of cut the seam, but it's in the same spot where I got the little bubble right there. That's just a coincidence, just the way things worked out. So now to measure current, we got to put the current through the meter, but we cannot exceed the setting that we set. So all I have to do is set it to milliamps because it's an auto ranging meter. I don't have to move the red probe for anything but high current. We're not measuring high current in this video, just milliamps of current. I believe this has a maximum of 600 milliamps of current. Check the owner's manual for user manual, whatever, for the meter you're using. But in any case, we cannot like measure the supply voltage now. I can because I limited the power supply voltage. We won't damage the meter. But if you have a voltage that will give you basically unlimited current, that will blow a fuse in the meter. And so we're going towards the more negative side with black, and with the red we're coming over here. We don't have to, but we are. So there you can see, we expected, because we got more than 3 volts across the 1000 ohm resistor, so we expected a little bit more than 3 milliamps of current, and you can see that right there. If you do get these probes backwards, that's not a big danger. You just get a negative current on there, and there you can see negative current. Same happens with voltage, and no big deal. With resistance, there's no direction that you got to go. So now we definitely want to get this off of measuring current. We're all done measuring current, and that's the main way you can blow a fuse. So we're setting this to resistance right there. Again, it's auto ranging. If there's numbers, set it to a number higher than you're going to measure, but you know, you're not going to damage anything if something has more resistance than what you are setting. So we have a break now. So all we got connected to the resistor is the positive supply over there. There's no voltage across it. It's a dead end, so we can measure the resistance. Doesn't matter which direction, it is not polarized. And there you go. So you see it took a little while. What it was thinking of what range it has to set. So now it's in kilo ohms, a little less than 1 kilo ohm right there. So that's another reason why we might have a little bit more current than we would expect. This particular resistor has a 1% tolerance, and so I think we did. I think that's a 1% right there. But in any case, it can be 1% higher or lower, and then you know, there might be off a little bit from the measurement, but this should be fairly accurate. It's a cheap resistor though, so it may be more off than what its rated value is. But again, it was really close to 1000 ohms, so that's the main thing that matters. These are not precision components or anything. Things are going to be off a little bit, but that's okay. That's to be expected. So this means out of limit, there's who knows how many hundreds of millions of ohms between these. I think this measures up to oh, I think it measures up to 10 million ohms. So who knows what it is, but it's out of limit. So if you see that when you're trying to take a measurement, good chance you're trying to measure an insulator or something, not a conductor or a resistor. So in any case, again, these videos that I've been making recently meant for absolute beginners. So I explained a lot more than I normally would, and I'm not sure where I put that jumper. I think I put that jumper away. That was in the middle of bridging the gap, so I'm not going to put it back there. It was connected at the beginning of the video, and the LEDs were lit up, of course. But in any case, rambled on long enough. Thanks for watching. Make sure you check out one of the other videos I'm posting to the screen, and check out links down below. They all help out a lot. I'll see you in the next video.